Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to have here today Karina Passariano. She's actually visiting for 3 days, and today she's talking about testing, and on Monday there's another talk on verification. So she works at NASA Ames, and I'll just let her do the talking.
Okay, thank you for the presentation, and thank you for inviting me here. It's a pleasure to be here, as usual. So I will talk about a tool that we have been developing at NASA Ames for the past 2 years, and we call it Symbolic Java PathFinder, and basically it performs symbolic execution of Java bytecode. And most of the work that I'll present here is also described in an ISTA paper that so it will also be presented next week. But there the focus is basically on combining unit level symbolic execution with some system level concrete execution or simulation. While the talk here will be more about the tool itself, and I'll talk a bit about this combination. So the ISTA talk will be slightly different. And this is work done by many people. I listed them there. So my colleagues at NASA Ames, Peter, Hank, Karen, and Mike. Also Suzette Person, who is a PhD student at Nebraska, and Mark Papi, who is at NASA Johnson Space Center. So the objective of our work is to develop automated techniques for error detection in complex flight control software for manned space missions. So it goes without saying that such software needs to be highly reliable, since it may lead to loss of life. So of course there are many solutions to this problem, and I just give a high level and perhaps naive presentation of these kind of solutions. So there is model checking, which is automatic, exhaustive, but it suffers from scalability issues. Then there is static analysis, which is automatic, scalable, and exhaustive, but it may report too many errors that are spurious. And also there is testing, where the reported errors are real, but it may miss errors. And testing, of course, is widely used at NASA and elsewhere, and actually it is the technique for checking software, at least at NASA. So we found that the easiest way to sell our formal verification techniques is to package them in a way that we tell people that they help them in the testing process. So this is the easiest for us to sell our techniques. So basically, our solution is to combine the strengths of model checking and static analysis techniques, and in particular we use a well-known technique which is called symbolic execution, that is also used here, for example, in the PEX tool and many other tools. So to combine the strengths of these static techniques to help testing. So to combine basically static techniques to help the dynamic verification techniques that are used at Ames. And we developed Symbolic Java PathFinder, which combines symbolic execution with model checking and constraint solving for automated test input generation. And it generates test suites that obtain high coverage, and it allows the user actually to define the coverage metrics. Usually they are structural coverage, like branch or statement, but also predicate coverage, as Tom Ball proposed several years ago. And also during test generation, our tool also checks for errors, because in fact we use a model checker as the underlying engine for our analysis. And perhaps equally important is it's freely available. So Java PathFinder, the Java PathFinder tool is available from SourceForge, and Symbolic JPF is basically the SymBC extension. So you can look at it and use it and extend it yourself. So just a quick overview of Symbolic JPF. It implements a non-standard interpretation of bytecodes, and it enables the JPF model checker to perform a symbolic analysis. And I'll give more details about that soon. And the symbolic information is stored in attributes which are associated with a concrete program data. And these attributes are propagated dynamically or on demand during symbolic execution. And I'll explain what that is. And right now it handles mixed integer and real constraints using some off-the-shelf constraint solvers. It also handles complex math functions, because this was basically a requirement for our projects. So we put quite a bit of effort into that. And also it can handle preconditions and multi-threading, because it uses JPF as the underlying analysis engine. And also it allows for mixed concrete and symbolic execution, in the sense that you can start symbolic execution at any point in the program and also at any time during execution. So basically you could trigger symbolic execution based on some condition on the program state or the depth of the search or things like that. And it allows dynamic modification of execution semantics, and I'll explain what that is. So this hopefully ensures a low overhead of these symbolic techniques. And I'll explain more what it means. We can change midstream from concrete to symbolic execution. And we have applied our tools to many software systems now, but I'll describe the application of our tool to testing a prototype NASA flight software component, where we helped to find a serious bug that resulted in design changes to the software. So this is just a very high level of description of model checking versus testing and simulation, but of course people here know about these things, so I'll just go quickly. So basically one can model a system, can view a system as a finite state machine, or okay, it might not be finite. And then simulation or testing checks only some paths through this machine, and then it maybe compares this path to some specification, and it reports that the specification holds or not. While in model checking, at least in theory, it tries to exhaustively explore all the paths through the state machine, and also it compares them against the formal specification. And then the result is either that the property holds or there is an error trace. So in particular for our work, we use a model checker, and it is an explicit state model checker, similar to the spin verification tool, for example, that Gerard Holtzman developed. And what it does, it is built on top of a custom-made virtual machine. And the focus of Java PathFinder is actually on finding bugs rather than proving properties, which is hard, if not impossible, for Java programs. And it focuses on concurrency-related bugs like deadlocks, races, missed signals, etc. Also, it can check for Java runtime-related errors like unhandled exceptions, heap usage, and so on. And it can also check for user specified assertions. And there are some other mechanisms, so we can use listeners to check for safety properties encoded as finite state automata, as monitors basically for the execution. So JPF uses a variety of scalability mechanisms, and I just listed them here. And this is a bit of publicity for it, so it received some awards in 2003. It is now publicly available, and it has been used by people outside NASA. For example, Fujitsu has applied it for a big web application that apparently has 1 million lines of code. So I'll also give a bit of background on symbolic execution. So this is a technique proposed by James King in the 70s, and I think Laurie Clark at the same time proposed similar techniques. And the idea is to analyze a program with unspecified inputs by executing the program in a non-standard way with symbolic rather than concrete inputs. And then the symbolic states represent sets of concrete states. And for each path that is executed during this non-standard analysis, one also builds a path condition that encodes the condition on the inputs for the execution to follow that path. And one usually needs a constraint solver or a decision procedure to check the path condition satisfiability. And the idea is that once the path condition becomes unsatisfiable, the search should stop on that path, because there are no inputs that could lead the execution on that path. So the symbolic state has symbolic values and expressions for variables rather than concrete values in the concrete standard execution of a program. It also remembers the path condition and, of course, the program counter. And this is just a quick example of symbolic execution as contrasted with the standard concrete execution. So let's say we have this code on the left. The inputs are integers x and y, and then we have if x is greater than y, some code that actually swaps x with y. And we want to check if this assertion is reachable or not. So how one would do testing for this code she would start with concrete values, let's say 1 for x and 0 for y, and of course it will execute only one pass through the code, on which it happens that the assertion is not reachable. While with symbolic execution, one will have a symbolic execution tree rather than just one trace. And the execution starts with symbolic values rather than concrete ones. So for example, in the initial states, x and y are big X and big Y. They represent some symbolic values, and also we have a path condition that is initially true. And then on each branch, the path condition is updated according to the condition that is followed through the code. So on one branch, the path condition is X is less or equal than Y, corresponding to the else branch here. And on the other one, the path condition X is greater than Y. And then symbolic execution computes all these expressions in terms of the inputs. And on the second if statement, if X is greater than one path is feasible, but on the other path, actually a constraint solver will, or a decision procedure will detect that this is unfeasible, so we can also prove that this assertion is unreachable. So in principle, if the program has no loops, you can also prove properties. Of course, if you have loop recursion and things like that, you need more powerful techniques to actually prove properties. But as I said, we use this tool mainly for testing, for test generation. And as I said, the path condition basically encodes the constraints on the input to reach that point in the program. So in order to achieve coverage of a particular statement, basically you need to solve the path condition that you obtained at that statement, and you would obtain the actual inputs to obtain that coverage. So basically this is what we do, and this is a classic approach that many other people do. So now what we do in Symbolic JPF, basically we use, as I said, the search engine of the Java PathFinder to generate and explore this symbolic execution tree. So JPF also is used to analyze thread interleavings and other forms of non-determinism that might be present in the code. And we don't do any state matching because this is in general undecidable, but actually this summer we are working with a student to look at possible abstraction techniques to do some kind of abstract subsumption checking for the symbolic states that are generated during symbolic execution. But for the purpose of this presentation, simply we limit the possibly infinite symbolic state space search by either limiting the search of the model checker or putting a limit on the number of constraints in the path condition. And we use off-the-shelf decision procedures to check the path conditions. And the idea is that whenever the path condition is passed to the constraint solver, and if the constraint solver reports that it's unsatisfiable, the model checker is instructed to backtrack. So it abandons searching along that path. And we have incorporated two constraint solvers, Choco and iSolver. Both of them are pure Java. So this was the main advantage because we develop it. We are several developers, so we wanted to have something that runs on any platform. But they are quite fragile. And we have, as I said, quite a bit of pressure in our project to try to handle constraints on reals, and also mixed linear and nonlinear constraints. And this summer, again, a student has been working on integrating CVC3. And the goal is basically we have a common interface to different decision procedures. So the idea eventually would be for the user maybe to select which decision procedure to use based maybe on the application domain and things like that. So a little bit about the implementation. The key mechanisms that we used were JPF's bytecode instruction factory, which basically allows you to replace or extend the standard concrete execution semantics of bytecodes with non-standard symbolic execution. And this actually can happen even at runtime, but we didn't use this feature. And as I said, we also use these attributes. So basically we store all these symbolic values and expressions that are generated during symbolic execution in so-called attributes associated with the program variables, fields, operands, and so on. And they are actually propagated along the concrete values. So I'll talk a bit about that. And they are propagated as needed during symbolic execution. Now, I'll show an example what I mean by that. And we also used other mechanisms that were present in JPF. One is choice generator. So basically we use a special construct that instructs JPF to make a non-deterministic choice, to branch the search in the cases where we evaluate branch conditions in order to consider both the if and then parts of a condition. We also use listeners for printing results of symbolic execution. So listeners basically are like little monitors that monitor the execution, and they can collect data about the execution and things like that. And they can also influence the execution. So for example, they can be used to change these execution semantics from concrete to symbolic. And we also have a mechanism which is called native peers. So the idea is that you have some native libraries that cannot be handled directly by JPF. And then you need to model them somehow to enable the analysis. And we used it, for example, to capture math library calls, all the trigonometric functions and things like that. And because Choco and iSolver handle these constraints, we pass them directly to the constraint solver. But for example, for CVC3, I'm thinking we can use maybe uninterpreted functions. So at least to do something about them, because there is interest in this particular So we need to model them somehow. But of course, the same mechanism could be used for modeling all the other libraries that basically fall outside our analysis scope. So I'll just give a bit more information about the various techniques that we used in our implementation. So as I said, we use an instruction factory for symbolic execution of bytecodes. So basically, in JPF itself implements a concrete execution semantics, and it uses a stack machine model. And for each method that is executed, it maintains a set of instruction objects created from the method bytecodes. And I'll give some examples. So what we did, basically, we created a new instruction factory that does this symbolic execution, and basically it contains instructions for the symbolic interpretation of bytecodes. And they are derived from the JPF score, so actually we add only conditionally new functionality, and most of the bytecodes actually remained unchanged. And this allows us to do this concrete, simultaneous concrete and symbolic execution. And based on the same model, one can build his own non-standard interpreter. Let's say if you want to do some form of abstract interpretation or to collect other forms of information, you could use this as a model to implement your own analysis. So I'll talk a bit about these attributes. So basically the program state in JPF maintains a call stack per thread, and then there are stack frames per each executed methods, and each stack frame maintains the locals and operands, and also there is the heap that has the values of the fields, basically, and also you have scheduling information. So what we did, we used a previous experimental extension of JPF that used slot attributes. So basically these attributes can be used to store additional information besides the actual concrete values of the locals and the operands on the stack frame. And we generalized this mechanism to also include field attributes. And as I said, we use them to store the symbolic values and expressions created during symbolic execution. And actually, attribute manipulation is done mainly inside JPF core. So basically, when you do an assignment, JPF, let's say the core would know to also transfer the attributes. So we also needed to worry about instructions that create or modify symbolic information, like numeric, compare and branch, and things like that. And I just want to emphasize again that now this mechanism is general enough to enable one to just do other kinds of analysis. So in some sense we have a general framework that could be easily customizable for other kinds of analysis. And for example, one can keep track of the physical dimensions of the data and maybe throw an error when you add meters with feet or something. And also one can also perform a Dart-like execution, basically a concolic execution, because we have, it could come almost for free in our framework, but we can discuss more about that. So we have separately the concrete data, and all this symbolic information, all this meta information is kept in these attributes. So I'll just talk a bit about handling branching conditions. So if you remember from that little symbolic execution tree, symbolic execution of branching conditions involves the creation of a non-deterministic choice in JPF, and then creating a path condition associated with each choice. So on one choice you would add the condition, and on the other one its negation to the path condition. And then we would check satisfiability with some constraint solver, and if unsatisfiable, we instruct JPF to backtrack. And basically I just put here a bit of code about how one can create such a choice generator. So we created a special PC choice generator that we'll have basically two choices, let's say, for a condition, and then in an array it will remember pointers to the path conditions on both choices. So just a bit of an example of how we model IAdd. So this is a bytecode that adds two integers, and on the left hand side I have the instruction for the concrete execution. So basically how one executes IAdd, it will first pop the two values from the associated stack. So please ignore this extra thread info information. And then it will push back the value on the stack. This is more or less what it should happen. And then it will return the next instruction to be executed. Now in the symbolic execution of IAdd, what we do first, we first get the attributes of the first two slots on the stack, and if they are null, it means the values that flew into this instruction were concrete. So then we can simply do the concrete execution, and as we would have done it before. But on the else branch, we notice that this is symbolic, so we just pop the values. And then basically we need to push back the result and set the attributes of the result to an expression that represents now the addition of these symbolic values. So I'm not sure, maybe it's a bit too much information, but here we just pushed back 0 because we say in symbolic mode we don't care about the concrete value, but in a concolic or this mixed concrete symbolic execution, one should push here also the value v1 plus v2. So in this way you could maintain both concrete and symbolic values. But yeah. Okay, so now for another example of a conditional. So let's consider here this if g bytecode that basically compares a value with 0, and if it's greater or equal than 0, then it will go to some target, otherwise it will execute the next instruction. So basically this is the concrete code. So here what happens is in a condition you pop the value from the top of the stack, and if it's greater than 0, you set the next instruction to be executed to some value, otherwise to the next instruction, and return. And this is the corresponding symbolic code, symbolic execution, the code for the symbolic execution of the same bytecode. So again, what we do, we first look at the attribute of the first value on the stack. If it's null, again, it means that there is no symbolic value that needs to be handled here, so we just simply delegate this to super, and otherwise we create a choice generator, and basically we instruct JPF here to make a choice, and then when it returns, so there is a bit more code here, but JPF basically will execute this code twice, and on one branch the condition will be false, in which case we update the path condition with the corresponding constraints, and on the other branch it will be true, and we do again an update, and then we invoke JPF. We invoke a decision procedure on the path condition to see if it's satisfiable or not. If it's not, JPF backtracks, otherwise continue execution. So hopefully this will give you an idea of what is happening here. Everything happens in this non-standard interpretation of the bytecodes, and I said before that these attributes are propagated on demand. So this means that we don't assume that all the instructions are executed symbolically, but rather we start execution with some symbolic attributes, and then we check, and these attributes will be assigned maybe to more variables, and it will flow into the code on demand. So this is a bit different from our previous approach, where we used basically it was based on code instrumentation, and there we instrumented everything. So in some sense it was less efficient. I'll talk more about that. So this is...
What does that PC do? The next to last statement at the bottom?
Yeah, so here we associate with the choice generator the current path condition. So basically what happens on the current path, we remember all the choices. So there is more code here, but then we create a new choice. We get the path condition from the previous choice, we add the new constraints, and we associate it with the current choice. So the backtracking would happen here, that basically the PC, the path condition, is unsatisfiable. If it is satisfiable, then it means we need to remember it. And this is the mechanism that we use to remember it. We associate it with the current choice in the search. Yeah, sorry.
So does something similar happen for exceptions too? So when you the division instruction, does it check whether we divide by 0?
Yeah, there is some code we can do more, but by the way, division does have that. So what would happen here is, yeah, I think we introduce. I can show you in the code, but in division, by the way, we check if the path condition allows you to have a division by 0 or not, and then on one path we throw an exception. So in principle you could do that for more things, but we don't. We check for division, yeah.
Does that also mean that in subsets you're currently doing depth first search with the backtracking, or do you have arbitrary search strategies?
Yeah, so here basically we tell JPF ignore next transition. So it would work, JPF has a different search heuristics, and it would work with other search heuristics. So we made it work. It will just backtrack to some other state that it remembered. So you can store the states, but they wouldn't be used for state matching. And then you could have different search strategies. So just here I put it because I also gave this to talk to some other audience. So basically this is how you run the tool. Now it's completely, let's say, push button, in the sense that you don't need to touch the code, so you can just instruct JPF from the command line or giving it a run configuration. So basically in order to analyze symbolically method which is called unit under test, let's say, in a Java program called main. You just specify this. You specify maybe some methods are concrete, some parameters are concrete, some parameters are symbolic. You can have more methods here. And then you specify the constraint solver. Here you instruct JPF to use the symbolic peer packages for the math library or for whatever model libraries that you have. And also this listener will print the path conditions and then the method summaries in terms of inputs and outputs. And this instructs JPF to use the symbolic instruction factory. So this would be the easiest way to use our tool. Yeah?
What does it mean to leave a parameter concrete? Is then a concrete choice performed on that value, or is it just 0?
So what happens here, just if the parameter is symbolic, then we just inject an attribute, which is a symbolic value. And for the concrete one, you just leave it concrete, so the attribute will be null.
You need some concrete value, or maybe different.
Yeah, but this is a method that is reachable in an executable program which is called main. So in some sense we don't need a test driver or anything, but you need a program that at some point will reach the execution of unit under test. So this is what is happening, and it will use the concrete value that just came to, that just happens to flow into the execution. And then we are working on, so of course there are more things here. So we are working on generating test sequences, what happens with recursion. So there are many things that we didn't figure out yet. But yeah, we can talk more about this. And you can also specify preconditions and input global fields via user annotations. And you can imagine with preconditions, they would simply be used to initialize the path condition with those constraints rather than starting with true. So now, I'll go a bit now more into the topic of the ISTA paper. So first of all, this tool, I believe that is most effective. So although it is general enough to work on any program, it's most effective at unit or subsystem level because of inherent limitations, like the power of the constraint solvers that we use, and or the number of constraints that can be handled. So we think that the power of this tool is that we can combine it with a concrete execution at the system level. So our idea is to start execution in a concrete mode, and then to maybe when you reach an interesting state, start this symbolic execution. So this is illustrated here. So basically we say that can start at any point in the program, can use mixed symbolic and concrete inputs. And as I already said, no special test driver is needed. It's just sufficient to have an executable program that uses methods, or the method or code under test. Please, sorry.
Well, concrete here means you are still running a path with JPF.
Yeah, so you just run it concretely, maybe multiple paths.
But I mean, to truly achieve better. So I wonder, to what extent can JPF actually run any program concretely? Isn't it still?
So to the extent JPF runs a program concretely, then this slide is about that.
Right.
We have another slide that talks about something else. So now, basically, as I said, this concrete symbolic execution can be triggered anytime during concrete execution. So one, for example, can use a specialized listener to monitor the concrete execution and trigger symbolic execution based on certain conditions. So the advantage of this method would be that you can do unit-level analysis in realistic contexts. So basically we can use effectively the concrete system-level execution to set up environment for unit-level symbolic execution. And maybe this doesn't look too much, but actually if you consider inputs also data structures or arrays, I think this becomes non-trivial, and we can discuss more about that. So we are working on that. And just some applications.
So, the way I understand your symbolic execution, you backtrack during symbolic execution.
So we use this model checker that just goes enumerates paths or state during.
So if the system interacts with device states, you wouldn't be able to backtrack.
Yeah, so that's why I mentioned those models. So you need to model them with those peer methods. You need to model them in order to consider them. You need to provide an abstraction for them. I agree. Yeah. So we re-execute the program in our specialized execution environment on which we have full control. This is what is happening here.
But prior to symbolic execution, it will interact with device state, and then during symbolic execution, it will switch to the model.
Sorry, no, even in concrete mode, if you run it in JPF, you would still need a model. Okay, so then some applications. So basically, you can exercise some deep system executions, like you can let a server run for many iterations and then trigger symbolic execution, maybe to find something suspicious. Another idea for this would be to extend or modify existing tests. For example, we did some work in the past for test sequence generation of Java containers. So their test sequences are basically, let's say, methods that add or remove elements in a container. And let's say you have a test suite, but you are not happy with the coverage. So you can run a sequence in concrete mode, set up the state of the heap, and then try to run again an add or a remove in symbolic mode to see if you can increase the coverage. And we believe this could be effective. And one of our collaborators, Mats Heimdal from University of Minnesota, he also saw this framework, and he said he had, for example, discussions with people at Boeing, and they are interested in generating tests that are similar. So let's say a test basically, I think it was for some user panel that tests if some buttons are on and off, and they would, he was saying that random test generation was not good, because they just wanted basically the panel to look the same and maybe certain feature to be different, so that it looks familiar to the users that, let's say, would want to test such a system. And one could use this again, so you could take an existing test and just vary certain parameters and obtain variations of that test using this approach. Yeah, sorry.
Could you handle time?
Time? Java real time? What? You can model it. If we can model it. No, so one would need to model it to have a model of time and do things like that. Yeah, I think actually there is somebody, Howard Barringer, who used JPF to model some real-time features with Willem Witzer, but yeah, I don't know. Okay, so I'll just talk a bit about this case study, which is called the onboard abort executive. So this is a prototype for crew exploration vehicle ascent abort handling, being developed at the Johnson Space Center for the guidance, navigation, and control system. And the test generation was done by hand by the engineers, and they gave us this component to see if we can do better. So basically, they require different kinds of requirement and code coverage, and I'll talk a bit more about this. So first of all, I'll just give you a high-level description of the system. So given a test of inputs, the software checks a set of flight rules that are basically supposed to be invariants of the flight. And if one of them is violated, then the mission needs to be aborted. So let's say if one or multiple flight rules are violated, then you need to select the feasible aborts. So there may be several of them. And then you, depending on the status of flight and things like that, and then it picks one of the aborts to be issued. So in some sense, this was, it was not very big, just 600 lines of code, but very complicated conditions, up to 60 constraints in an if statement. So it was in some sense the ideal application for symbolic execution. So basically, these are our results. So manual testing was time consuming, and it could not achieve all the coverage that they wanted. Guided random testing could not cover all the aborts. So actually, random testing performed poorly on this application just because it has very many complicated constraints. So it's a typical application where random testing doesn't perform that well. We had however, other studies where random testing performs pretty well. So we were able to generate tests to cover all aborts and flight rules. And we found some errors, for example, flight rules broken but no abort picked. And actually, this was fixed. And what they did, they used our tests for regression testing for the next generation of their code. And then they found a major bug in the new version that affected several modules. So it was quite a bit of a success for us. And I should just say that for me, actually, it was an interesting experience to collaborate with the people at JSC. So because it gave me some insight into the power of our automated tool. So initially we generated a minimal set of test cases, I think around 30 test cases, and they were violating multiple flight rules. However, the developers were not happy because they said, no, this component runs under the assumption that it cannot handle, it can handle only single flight rule violations, and later will try to handle multiple flight rule violations. So we needed to modify the search to basically, we put flags, and whenever a second flight rule violation happened, just to backtrack, because it was simply not interesting for them. So they just wanted tests that led only to one flight rule violation and one abort. This was the current mode. So again, this gives an idea of, it's not enough just to generate test cases that achieve good coverage. They also need to mean something for them. So this is an example of the test cases, and actually we generated, so basically one test case says it covers some flight rule and it issues some abort, and then it has some values, and okay, this model has time, but their time, and actually we generated these test cases in a format that they could use in their simulator. So basically they just took them and they ran them through their simulator. So this is how they validated our tests. And this is an example of constraints. So as I said, there are many constraints on in the path condition. Okay, so another interesting outcome of this collaboration was that basically we looked at this component in isolation, but this is part of a bigger control system that interacts, and right now they are running it in this simulation environment that has models for physical laws and things like that, but we analyze it in isolation. And for example, we generated a test case where the inertial velocity was the maximum value, but the altitude was 0. And the developer joked and he said it must have been a really bad day, or you started from the Death Sea or something like that. No, so from Death Valley, below altitude, because basically you cannot reach the maximum velocity at 0 altitude. So the idea is then that one would need to encode these constraints explicitly. But of course the developers don't want to encode any constraints explicitly. So then we actually collaborated a bit with somebody else from our group, Karen, who runs many Monte Carlo simulations on the whole system. And then our idea was to basically use these simulation runs to get some data correlations and to use them as preconditions to improve the symbolic execution. And we did some preliminary experiments for that. So for the simulation environment, we used Antares, which is Advanced NASA Technology Architecture for Exploration Studies. And this is how we used it. So basically, let's say we have the whole system, and the unit, like the OAE, is just part of it. So the idea would be to run many simulations and to monitor the inputs to the unit, and then to run some correlation analysis and obtain the precondition. And for this, and Karen is using a treatment learner. I don't know too much about it, but it's able to determine ranges for variables. But one can imagine can also run DICON or other things to determine likely preconditions here, and then to run a more precise symbolic execution. Now, of course, there is another problem, that these correlations are just only likely. So if they don't hold, you are likely to miss important behavior in your unit. So at least what we did here with these ranges that we got from Karen, we added some delta values to increase a bit the envelope of the preconditions obtained from her. And in this way, we obtain more precise test cases, more meaningful test cases for them. But we need to do more work for this. Okay, so I'm almost done. I'll just have a brief comparison with our previous work. So we had the previous framework, which is in the symbolic extension of on SourceForge, and we called it JPFSC, so for lack of a better name. And that one worked by code instrumentation, and it was only partially automated. So the idea there was to instrument the source code or the bytecode to perform this non-standard execution. So this was quite general, and actually the methodology that we defined there could be used with any model checker that has the ability to backtrack, basically. But it may result in suboptimal execution, meaning that for each instrumented bytecode, JPF needed to check a set of bytecodes representing the symbolic counterpart. And it also required an approximate static type propagation to determine which bytecode to instrument. And Saswat Anand, who was here last year, he implemented such analysis. So now in our new framework, this is no longer needed since the symbolic information is propagated dynamically. So you wouldn't need to have this approximate analysis. So we always maintain the most precise information about the symbolic nature of the data. However, we did not really do a comparison between the two frameworks, so we didn't do an empirical evaluation to see which one is better or not. All I can say is that this new framework is fully automated, and this is the focus of our work now. So in JPFSC also had the technique to handle input data structures and arrays, and we called it lazy initialization. So basically it used some form of lazy evaluation technique to start with an uninitialized knowledge about the heap, and then to lazily add information about the heap during execution. And actually we are moving this algorithm into symbolic JPF this summer with a student from Nebraska, Suzette person. And also we are working on adding multiple decision procedures. As I said, actually we added CVC3. And we also used this previous framework for generating test sequences and many other applications, and we plan to add that to our current framework. So I just listed a bit here the related work. Of course, there is a lot of it. So of course, our work is related to using model checking for test input generation, and also to extend the static checker, although we do the classic symbolic execution, while I think ESC does not King style execution, but very similar. Maybe you can say more. Then there is this tool Simstra that of Tao Z and others that performs a dedicated symbolic execution for test sequence generation, and it also performs symbolic subsumption checking for symbolic states. So it handles only integers, so it's a limited tool. Then also there was a previous approach, SymClat, that tried to implement a symbolic execution in JPF via changing the bytecodes, but it did not use attributes and the instruction factory, so it used a different mechanism for doing that. And then there are other techniques, Bogor, which is a tool from Kansas State, which is similar to our previous approach, JPFSC. And then there are these tools, Dart, Qt, PEX, that perform a symbolic execution along a concrete execution, while at least with what I presented here, we can use concrete execution to set up the symbolic one. So, and there are many other things. Since we use JPF, we don't need to do re-execution, so we can just backtrack, and there are many, let's say, little technical differences. And of course, because we use JPF, we can handle multi-threading for free, so it's orthogonal to what we are doing. And this is also related to the work of Kadar and Engler. And there are other hybrid approaches that are similar in spirit, in the sense that they combine static and dynamic analysis techniques, but they are quite different from in the methodology that they use. So in conclusion, I presented symbolic JPF, which performs a non-standard interpretation of bytecodes, and the symbolic information is propagated via attributes, and it is available from SymBC extension on SourceForge of JPF. It allows anytime symbolic execution. I talked a bit about integration with system-level simulation, and also I talked about an application to a prototype flight component where we helped finding a major bug. And current and future work, we are doing a test generation for UML state charts and also simulating state flow and embedded MATLAB models through a collaboration with University of Vanderbilt, and they are writing a translator or transformation tool from such models into Java so that we can analyze and also do test case generation for them. We are having now more applications at NASA in different other projects. So one application is for SHINE, which is a health monitoring program, rule-based health monitoring program, which is translated again in Java, and then we can analyze it. Another application is for some aero project that does tactical separation assisted flight environment. And also we have some Java code from Johnson Space Center for mission operations that does the ground software. So we are trying to apply our tools to many applications. And then we have at least one external client that we know who they use the symbolic execution, I think the old version, to check some web applications. So we are working on, we are planning to work on a tighter integration with system level simulation to incorporate more decision procedures. And also we use symbolic execution for differential analysis, and we have a paper at FSC that will appear later this year. So the idea there is to compute the logical differences between two versions of a program, and then to use that for different things. For example, to test cases, to generate test cases that exercise only the changed code in the new versions, or to check logical equivalence after software refactoring, or they can be used as formal documentation and so on. Then we are also working on a generic language for defining coverage. So we also want to look at MC-DC coverage for these models. So our clients are interested in that. And we would like also to use that look at parallelizing these algorithms, because obviously symbolic execution is, I don't know what the term is, embarrassingly parallel. So one should do that probably. And then we have so JPF is part of Google Summer of Code this year. So Google finances students to contribute to open source projects. And I'm working with two students. One is working on implementing this generalized symbolic execution in the new framework to handle input data structures, arrays, maybe other things. And the other student, Misun, a student of Tao Z, is working on generating and extending test sequences, and also he's looking at different abstract techniques for state matching. So this concludes my talk. Thanks.
Parallelizing symbolic execution, you mean the search?
Yeah, we didn't look at it, but it should be just, just...
The search itself?
Yeah, just putting it on two computers. The search in our symbolic execution.
Like this Sage, for instance, that we're using here, it's parallelized. We're running it on networks of MRT core machine for more than a year, etc.
Okay, good. I didn't know, but we should. Yeah, exactly. I didn't put it as a big idea. Just that it should be done. Yeah, sorry, maybe I didn't know, but yeah.
But the symbolic execution itself, which is actually quite expensive, that's harder. You see, for a single execution, that's what I mean. That would be hard.
Yeah, but we don't do this Dart-like execution, so we expand the whole tree, and this is easy to distribute because they don't really share anything, any information. This is what I meant. We can talk. Yeah.
Same path.
No. Yeah.
Because like with the stage, we have a single symbolic execution. Symbolic execution has perhaps 1 billion x86 instructions, 1,000 input bytes, hundreds of thousands of constraints.
I didn't mean that. Okay. Yeah. Yeah, I just meant exactly to distribute the tree, which should be.
For one single path.
Okay.
So how does the integration of the thread scheduler with the symbolic
It works naturally. So the thread scheduler is just another choice in the search, which is of a different type. So all we need.
You can schedule at all possible instructions.
Yeah.
Don't you get too many hops?
So it. You mean how it interacts? So JPF has some algorithms like partial order reduction, symmetry reduction. It tries to do some heap symmetry reduction. So with heap symmetry reduction, I don't think it should interact. With partial order reduction, we should think about it a bit. But just the scheduler is orthogonal, so it shouldn't interact with that. Does it make sense?
In the case study, you covered the different abortion code passes. So I wonder, maybe talk about it, I forgot, but were the loops in the program, did you have to define bounds, or did you kind of steer the search towards these coverage goals?
So this component actually had no loops. It was supposed to run repeatedly. So the loop was outside. So it was just basically a big monitor that would monitor many conditions and issue aborts if necessary. And it would be scheduled repeatedly. This would be the idea.
So you had to bound on the outer loop?
We just looked inside the loop. We had a second version that kept a bit of state from the previous iteration, and we modeled it. So we looked at most 2 iterations.
And then you did an exhaustive search in these 2 iterations, and
so we didn't do exhaustively. We just stopped when we achieved the desired coverage, which was all the possible flight rule and abort combinations. This is what they wanted.
So the search didn't try to actually reach the coverage goals, but if it happened to reach it, then it would stop there.
Yeah. Okay. In this particular application.
Okay. More questions? Otherwise, I think I'll speak again.
Thanks.